I'm going to start talking about the first lecture. It's called dynamic programming. History, a little bit of history. It was introduced in 1950s by a man called Richard Bellman. Since its development, it has been implemented in all kinds of areas. So it has vast applications, not just in control. In digital signal processing, in path planning. In all these kind of applications, it has dramatic impact for these kind of areas. This word here, programming, it has nothing to do with computers. Actually, as a matter of fact, at this kind of stage, this computers wasn't popular at all. So programming here means more planning. For example, if we are traveling, if I want to travel from the West Coast to the East Coast, I have to plan my trip. I want to go there in the shortest distance path. So that is programming here, planning the trip. So we have talked about some of these already, the history and then useful applications. I want to mention one point here, just to let you know how this thing is useful. So in IEEE Global History Network, so it's using this to describe dynamic program, a breakthrough which set the stage for the application of functional equation techniques in a wide spectrum of fields. So let's see how this actually works. Let me give you this one example to start with the discussion. So this is called a path planning problem. I have a starting node S. And I want to go here. This is the end node. And along the path, I have to go through several nodes, and I can make choices at different places. These numbers here, 1, 2, 3, 4, indicates the cost, in general, the cost for going each path over here. For example, if I'm traveling by air, this can be the distance between different cities, or the fuel assumption between these lines over here. So I'm going to go here from here to here in the minimum cost path. For this simple problem, you probably can figure this out after you look at this long enough. You can sort of list all the possible paths that you can do. But dynamic programming provides you one way to systematically do this. So this is a key idea. For this relatively complex and large-scale problem, dynamic programming provides you a collection of small problems. And by doing these small problems, you can solve this efficiently and then more systematically. Let us start with this observation here. Now, suppose your optimal path contains this node here, C here. Suppose this is one path on the one node on the optimal path. Forget about the starting point and this point over here. What do you think the path from C to E has to be? If this is the optimal path and this is one node on the optimal path. Yeah, that's correct. So it has to be C, D, E. It cannot be C, A, B, and E. You can definitely see this is more has more cost, right? So in a sort of more I would say professional language is this: if node C is on the optimal path, then there's a typo here. Then the remaining path from node C to node D has to be optimal. If I'm flying from West Coast to East Coast and I have stopped, for example, in somewhere in Minnesota, let's say, the remaining path from Minnesota to the East Coast has to be optimal. I don't want to stay in Minnesota for one night and then come back to San Francisco and then go to Boston. No, right? So this is what it's saying. The remaining path from here to here has to be optimal. This is the idea of optimal path planning. So if you buy that, let's see how this big scale problem can be broken down into small problems. So I'm going to define this. Dist E indicates the minimum cost from the starting point to this point. All right? So just to understand this, if I say dist B, it has to be the minimum cost from S to B. So in this case, you can see it is SAB. It cannot be SCAB. So the minimum distance from S to B is 7. So this is our notation, the notation we're going to be following. Now, look at this. The distance, the minimum distance, E. Now, there are only two possible ways to reach E. Either you go through B or you go through D. So the distance has to be coming from this combination of two. It's the minimum of these two. Either you start from node B, and then you have to or you start with the location D. And then if you started here, then your additional cost is 1. The only possibility is this. Now, over here, you have to use the distance to B and distance to D. Now, do it step by step. The distance to B, let's see, what's the minimum distance to B? There's only one possibility. You have to go through A, right? So the minimum distance to D is the distance to A plus this cost on this path. And the minimum distance to D, can everyone see this? Those sitting in the back? Good. All right. So the minimum distance to D has to be, you have two choices now, right? Either you go through B or you go through C. No other possibilities. So it's the minimum of, let's say, let me start with this one. The distance to C plus 3, this cost on this path. Or you go through B, then you add this path. Now you just do this step by step. Now you have to know distance, minimum distance to C and distance to A over here. I would say this is step 1, this is step 2, this is step 3. The minimum distance to A has to be, someone help me here. Yeah, you can see this is 1. But more systematically, if you let the computer do this, you would have to tell the computer this. It's the distance to S, which is 0 now you know, plus 1, or the distance to C plus this one, 4 over here. Now just one more step. Distance to C, now you already know the size, so I won't elaborate more. So it has to be 2. Now, doing this kind of steps, you can immediately, I claim, you can immediately know this thing which you wanted, the minimum distance to E. Because from here, now you know the distance to C is 2, the distance to A is 1, because this is 1, and this is 6, right? So this is the minimum distance to A. Now using these two, go back here, you know the minimum distance to D has to be what? 2 plus 3 is 5. Oh, I have to use the minimum distance to B, so I have to compute this guy first. Now, the minimum distance to B is 1 plus 6 is 7. Now we can do this. This is 5 because of this, and this is 8, so this is 5, right? Now finally come back here. B plus 2 is 9. D plus 1 is 6. Now this is 6. So we sort of started backwards. So we sort of started looking at this point. Okay, what has to be from here to here? What has to be the minimum? And then think about it. When we compute the actual path, we started off from this direction. This is how we compute. This is how we compute. And this is on this side. This is how we analyze. this is sort of intuitive, right? If you're going to anywhere, you wanted the shortest path. You always start at the end allocation to see where you're going to go optimal. Someone tell me what's the minimum path now by looking at this. So I have to, let me use another, so I can write it here. My end location is E, and then the previous node has to be, we computed this, it has to be D1. So it has to be this, D. And then from here, let's see where we can reach D in the minimum cost. It has to be this guy, right? Let me write down, let me highlight the shortest distance at each location. Okay, so here, the first step is, the second to the last step is D, and then C, and then what? Yeah, it's S, right? So that's how you can obtain the minimum cost and the minimum path. Sort of as a summary, this is how we did. This is what we did. All right? We analyzed the problem backwards, writing this down, E, B, D. And when we compute it, we do this forward computation, starting from C, A, B, D, E, right? So that's the idea of dynamic program, a very simple one. But in practice, this can be way more complicated and has lots of good applications if we understand the key concept over here. So this is Bellman's principle. As a summary, this is Bellman's principle of optimality. From any point on an optimal trajectory, this is very important. You have to be on the optimal trajectory. From any point on the optimal trajectory, the remaining trajectory has to be optimal for the corresponding problem if we start it at that point. All right. Richard Bellman is a very wise man. He attended Princeton at the age of 26, and then he finished PhD, guess what, in 3 months. But it has background, though. It's in the war, so there might be difficulties in various aspects. I don't know. He finished it. He made it. The reason I introduced dynamic program is because of this. We want to do optimal control. So as a sort of general optimal control problem, this is a statement, okay? Giving a general discrete time plant, xk plus 1 equals f xk, uk, and k. So I didn't specify any specific form of the system. It can be linear, nonlinear, or even time varying. And there can be state constraints, and this input can also have a constraint. This is way general than what we have learned in ME232, and it's more difficult. So the performance index is this. J is a scalar value, which is a function of the final state. This, I would say, the terminal cost at the final state. N is the final time, which we want to minimize this cost. And the function of this small accumulation of cost, starting from k equals to 0 to k equals n minus 1. This is the cost along the path, and this is the terminal cost. Okay? S and L are real scalar values functions. So our goal is to minimize this. This is what we want to do. Minimize J, obtain this optimal control sequence, U0 to Un minus 1. That's the problem. Now, as a matter of fact, you can see this discrete time LQ problem is a simplified version of this. Well, our system is a linear system, and our performance index is a quadratic performance index. These are quadratic functions of x. These are quadratic functions of u. Okay? This is a general problem. And as a matter of fact, this general difficult problem can be solved in dynamic programming. So let's see how it does. Actually, let me take a seat here. So whenever we have to do some sort of heavy math, I will write the detailed equations. And then I suggest you to also do that instead of reading the notes or handouts if you have it. Let's do this. General dynamic programming. Dynamic programming for optimal control. I'm going to define something for convenience. I'm going to define U, big U, capital U, as the control sequence from UK to UK minus plus 1 all the way to UN minus 1, big N minus 1. This is the cost. This is the control sequence starting from time k, UK plus 1, all the way to UN minus 1. Now, if you think about what we have done in dynamic programming, we sort of developed this notion of, we call it cost to go, which is saying this, J, K, let's say, the optimal cost to go, we are minimizing. So if we, suppose we start at time K, suppose we are starting right there, then what we want to do is we want to obtain this optimal control sequence that's going to minimize my cost, which is, if you see what I have introduced in the last slide, is this. Is this terminal cost plus this cost on the path. Okay, right? So this is the cost to go at time k. Now, think about it. And you can see this is valid. If I'm minimizing with respect to UK, then it's the same as this. Everything inside here is the same as this. This is because UK, which is defined here, is nothing but this small UK combined with this. Now you can see this is a capital U k plus 1. I have done nothing but redefining this control sequence over here. Now, if you do this, something interesting happens. If I'm minimizing, no, let me write it most explicitly. If I'm minimizing this whole thing here, I can take out the cost at time k. So I'm taking out one cost from this summation over here. And then the remaining part is going to be the same. Plus summation from, now it's from k plus 1 to n minus 1, and this L. I'm taking out one part from this summation here. Now look at this whole thing here. If I say I'm minimizing using this decision for variables u, k plus 1, if I'm doing this alone, will I be able to influence this guy? This thing depends totally on xk, uk, and k. But my control is for the future. So you can see this thing won't be able to influence this guy here. So that means I can take this minimization sort of thing to be inside and shift it over here. This thing won't be able to influence it. So more mathematically, this is what I mean. It equals to mean u, small uk, plus this minimization here. This is u, k plus 1. S, xn here, plus the summation from k plus 1 to n minus 1, and this L. I have to have another bracket. All right? Everyone sees this? Good. Now, minimizing from k plus 1 to this cost, what does this guy equal to? Exactly. It's j k plus 1 is the minimum cost if we start everything at time k plus 1. Now, writing this down, yeah, I can use this now. Writing this down here, okay? Then we have essentially solved the problem. We have written down this, which now you see is this. This is the optimal cost to go starting at time k plus 1. These two guys are equal. Now, just focusing on the original cost to go, and this last line over here, we have now the same thing as path planning. We have a sub-problem to solve. If we want to obtain this, then it's just about minimizing this one cost, optimal cost, plus this cost on this path. All right? This is exactly what you have seen earlier in the path programming, in the path planning problem. If we want to do minimization, if we want to obtain the minimization, we break it into small problems. Well, at each step, I'm doing a small minimization problem. If I'm doing this, then this is the optimal cost to go at the previous time step. So as you can imagine now, for sure, we can solve this problem just as simple as what we did in the path planning. So just a few final checkpoints. Doing this, the final time, at the final time, the boundary condition, which is if you seek the notation here, at time n, the final location on the path, it has to be minimum of this thing here. But when you are already there, you don't have this intermediate path. You only have this remaining final path. You only have this remaining final cost, right? So the boundary condition for this iterative problem is this. At time n is s x of n. Now, this one notion I have to mention here. If you notice my writing, I wrote it, the optimal cost to go at time k, see here, is a function of the state of xk. Similarly, when I wrote down here, the optimal cost to go at time k plus 1 is a function of x of k plus 1. I didn't write down anything else. Think about it. This is the same as the path planning problem. If I'm flying, let's say from San Francisco to Boston, and I have to stop at Minnesota, the minimum cost to go, if I start at Minnesota, is just a function of Minnesota. It's not a function of San Francisco, right? It's just the distance between Minnesota and Boston. Nothing else. The minimum cost has nothing to do with San Francisco. So it's the same thing here. The minimum cost is only a function of the current state. If it's k here, it's x of k here. K plus 1, x of k plus 1. Nothing else. So now, the problem can now be solved by solving a sequence of problems, starting from here to one step by step, going backwards to n plus 1, to n minus 1, all the way to here. That's the basic procedure for dynamic programming for optimal control. So I mentioned this is the tough problem. What we're going to mainly be focusing on is a simplified version, the LQ problem. Well, now I have mentioned this. L, it's saying I have a linear system. L means linear system. And Q is I have a quadratic cost. It's because these two notions are very important. It's only if you have this linear system and quadratic cost, you can obtain very, very nice solutions. Let's see. Let me read this again. I have written down also on the board over there. The system dynamics is this. A, B. Notice that I have, say, AK. So the system matrices can be time varying, no problem. And the initial state is x of 0. The performance index. Okay, all these system matrices, all these performance matrices in the performance index, they can also be time varying as well. This problem can be solved by dynamic programming. Some assumptions, just as a review, you might have already seen it. The performance matrix for X, the constraint matrix for X, has to be positive semi-definite. And the matrix for the terminal state has to be positive semi-definite. And this control matrix over here, R, has to be positive definite. Now, use dynamic programming. Where do you think I should start if I give you this problem? Correct, from n. And then I define this cost to go, right? Starting from time step n, I have to go backwards. Now, when you're doing this, this is what you're going to define. The optimal cost to go from time k is defined by this. It's the minimum of this guy. This is this comes from this summation sign here. It's the cost I have to pay along this path n. From time k to k plus 1. This is the cost I have to pay along the path. This comes from this summation sign over here. And then this is the optimal cost to go. Cost to go at time k plus 1. And then again, with the boundary conditions over here. This is at the final time, I only have this final constraint here. I don't have any additional paths, additional cost I have to pay. This is the definition of the problem. Now, as a general math review, I want to go through this kind of basic facts of quadratic functions. Consider I have a quadratic function, f, which is a function of u, which is it contains the quadratic term of u. It contains the linear term of u. Then it can contain some other kind of constant terms of q. Okay? If I want to minimize this quadratic function with respect to m, let's say m is positive definite. If I want to minimize this quadratic function, what will you do? Just as an initial guess. U is the variable, and this is the function I want to minimize. You can sort of have an intuitive idea. For example, if I want to minimize 2x squared plus 3x plus 7, what will you do over there? Take the derivative, right? And everything is the same here. If you want to minimize this, take the derivative of this function with respect to u. The only care, if you're not familiar with this, the only thing you have to be careful is how you take the derivatives. Let's review these facts. If I take the derivative of, I'm focusing on the second term here. If I want to take the derivative of p transpose times u with respect to u, all right? Let's say u is a vector of u1 and u2. Then if I take this derivative, it's nothing but doing this. I'm taking the derivative of p transpose times u, which is p1 times u1 plus P2 times U2 with respect to U. So I have two terms in U. So I'm taking explicitly with respect to U1, and then the same thing here. With respect to U2. So this is the result. Someone tell me what's the numbers here. If I take the first derivative with respect to U1, it is P1. The second, P2. So as a quick notation, it is P. Right? It's a vector P, a column vector P. Now, this first result can be generalized. If I'm taking the partial derivative of U transpose P, what do you think the result will be? I swapped the orders. It's exactly the same, right? You can either do this guy. You can write down what is this as a complete mathematical formula, or you can do this. U transpose P is a number. It's the same as P transpose U. They are both numbers, right? So you can do this. It's the same. Now with this, we can take a look at the first term. Partial U transpose MU partial U. So now I have two terms. I have two U's. Now if you remember the chain rule, this is what I have to. I have to take with respect to the first one, and then I have to add it up with respect to the partial derivative of the second. All right? So I have to do this. I have to sort of, let me say, I have to sort of regard the first, the second two terms together. And then I have to, when I do the second step, no, this is, when I do the second time, I have to do this, right? This is the idea from the chain rule. Now, if I want to do this guy, this is exactly very similar to this, right? Because U is a vector. M times U, a matrix times a vector, is a vector. So it's exactly the same as this. Consider P as the MU here. What will be the result? MU, right? And then the same thing doing here. What will be the result? M transpose U. So this is sort of doing this, okay? Now, I mentioned that M is a positive definite matrix. So in this class, when I say some matrix is positive definite, I'm assuming it's symmetric. So now, the final result is going to be this, 2MU, because M transpose is the same as M. This is the final result. So now with this, yes? Okay, the last one, right? Yeah, the student asked why this holds. I have two here. Let me give, for example, one example. When you do the derivative of, let's say, x squared, let's say, a simple case, it's x times x. Now, when you do the derivative, now you know this is very easy. Dx squared divided by dx. No, it's let me write it. Start a new page because I'm going to need it. When you do x derivative of this with respect to this, you know it's 2x, right? So this is the idea, okay? Now, if you x squared, you think about x squared as x times x. Actually, you're doing it twice. You're doing this dx first, then you have remaining x over here.
Yeah, that's right. But over
You mean this result?
Yeah, the p which is named is also function of p. So how do we write it? How do we write this equation mu? That p is not a constant here.
Yeah, p is not a constant. Yeah, so that's why we have two terms.
Yeah, so you assume n is univariate.
Mm.
Okay,
Yeah, come back to me if you want to know the details. But this is sort of as a easier way to get this to your mind. All right? Now we are here. Okay. Now you know how to take the partial derivative. Partial f respect to partial u. Okay, I have to say u ought, u not. Okay? So following what I have just done, the partial derivative of the first term is going to be mu naught, because there's a 1 divided by 2 here, so it's mu over here. And then the partial derivative of the second term is p, and the last term doesn't depend on u, so it's 0. Okay? So when you do this, now you can obtain the optimal control law. U optimal is you take this on the right hand side and then you invert this matrix. So you got to get this. Okay? This result is actually very useful, regardless whether I'm doing optimal control or not. This is useful in general. And then the optimal cost, if you substitute this guy inside this, you're going to get this. It's a quadratic function of p over here. Just put this back here. Now I'm going to immediately start using this fact of quadratic functions. For convenience, let me write the result down, because I'm going to immediately use it over here. You can take a look first while I'm writing down the result. So I got to do this optimal cost to go thing from n to n minus 1. All right? So I'm using the dynamic programming result. The optimal cost to go at time n plus 1 is this. Is the cost I'm going to have to pay at time n minus 1 to reach n, plus the cost, the optimal cost at time n, right? So this guy is a j n naught, just by previous analysis. Okay? Now you see immediately why I was doing that at the one slide earlier. This function, look at this one, it's a quadratic function of u with respect to some other terms. If I want to minimize this, I have to know how to solve that quadratic problem. So let me write this result over here. So if I want to do mean u f of u, which is 1 divided by 2 u transpose mu plus p transpose u plus q, and m is positive definite here. Then the optimal, which we have derived, optimal control is this. And the optimal cost is negative 1 divided by 2 p transpose mp plus q. Huh? M inverse here. Yeah. Okay. So I'm just going to use this. I can very quickly solve this problem. I mentioned this is a quadratic function of u. If I want to solve, when I write it as a function of x of n plus n minus 1. But I have an x of n here. So it is here we have to substitute what x of n equal to. X of n equal to n minus 1 x of n minus 1 plus bn minus 1 u n minus 1. So just substitute this system dynamics inside this quadratic function over here. Okay? You're going to get this. When I do that, substitute this inside, I'm going to have another quadratic function of x n minus 1, right? Because I have a quadratic function of x n here. So put this back here. I'm going to have this here. Quadratic function of x of n minus 1. This term is equal to this term here. And the rest of the terms are the same. Everyone sees this? Now look at this one. You can immediately apply this result here. If I ask you what is the optimal control law to minimize this quadratic function of u, quadratic function of u, here, quadratic function of u, what will be the optimal cost? Just by taking the partial derivative, we can obtain the result. It's got to be negative here, negative the inverse of the matrix that is staying in this quadratic function of u times the vector that is staying ahead of u over here, right? Just by using this result. What will be the matrix for the quadratic term of u by looking at this guy? This requires a little bit of observation. The quadratic matrix, the matrix staying in the quadratic term of u, first of all, this is 1, right? This one doesn't contain any function of u. Look at this one. What is the matrix that stays in the quadratic term of u? Right? So it's this term. It's this term and this term. When they multiply together, they will create a quadratic function of u. So the matrix over there is this. Now you have to transpose here. So it's u transpose b transpose times s times b, then u, right? So in total, you have this. The matrix staying in the quadratic term of u, it's got to be R plus this thing here. R plus B transpose S times B. Then take the inverse, just as what I did over there. Okay? Now, do it once again. What is the matrix? What's the matrix in the linear term of U? It's not going to occur here. This is a quadratic function. It's not going to occur here. It's occurring here, right? What is the matrix for the linear term? What's a vector, actually? It shouldn't be a matrix. It's a vector. What's a vector scalar inside the linear term of U? So it will happen if this term is multiplied with this term. It will also happen if this term is multiplied with this term, right? Now, just do it. If this term is multiplied with this term, what we're going to have? Okay, if this term is multiplied with this term, we're going to have x transpose n minus 1, a transpose n minus 1, s b n minus 1, u n minus 1. So that's the first term. This one combination with this one. And then this one combination with this one. I'm going to get u transpose n minus 1, b transpose n minus 1, s a n minus 1, x n minus 1. Now, someone just tell me, by observing this, are these scalars or matrices? This whole thing. This has to be a scalar, right? So because of the fact they are scalars, now you see, this is a scalar, so it's equal to the transpose of itself. Because it's a scalar, you don't get anything by taking the transpose. Now, if you take the transpose, you get exactly the same thing. X transpose, A transpose, S, I've told you S is symmetric, all right? Now, adding up, I have two terms of this. This is what you're going to get. Yeah, let me just write it down. Adding up, you're going to get 2. Let me see which order I want to choose. I probably want to choose, I want to choose the first one. So it's going to be 2x transpose n minus 1, yeah, A transpose n minus 1, S B n minus 1, U n minus 1. Now remember, there's a scalar 1 divided by 2 here. So in the end, this 2 is going to cancel. So that's why you're going to get this result here. It's the inverse of the M matrix, which we have just analyzed, times the, I've told you this one is going to cancel, times the vector scalar ahead of the U term, all right? It's a P over there. So take the transpose of this guy, you're going to get this. B transpose S A X n minus 1. All right, everyone with me? So this is the optimal control law for LQ at time n minus 1. Yes?
Sir, here you are assuming that all S, Q, S and Q, they are all symmetric.
Yes.
But if they are not symmetric, it's not dynamic.
If they're not symmetric, we have to do additional steps. Yeah. But as you think about it, when you are doing this kind of minimization problem, you want it to be symmetric, sort of, right?
Why do you want to be symmetric?
For example, take a look at this one here.
If S, for example, if S is not symmetric, we are imposing force on X2 rather than X1. Second element.
So one of the students asked about the assumptions of quadratic linear LQ problems. We say, for example, when we say x of k, let me use the constant q. The student asked about this thing. Student was concerned why this has to be symmetric. Take one example, for example. Take one numerical example. If this is not symmetric, let's say 1, 1, negative 3, 0. And then this guy is going to be equal to x1k squared plus x2k squared. Then you have some kind of combination term between x1k and x2k. Right? Just when you are designing this, it gives you less intuition. If you are minimizing a state, if you're minimizing, let's say just as a simple case, if you're minimizing this, it's less intuitive if you do this way. Because you want to say, for example, the states, you're minimizing the states. All right? Now you're doing this combination term. I'm not saying this is not possible. It is actually possible. And we will do one problem like that. Yeah.
Yeah, but it has, for example, if that minus 2 was 0, the intuition is that we are minimizing both x1 and x2. But here, we are minimizing the combination of x1 and x2, something like that.
Yeah, yeah. So that answers your question, right? Yeah. Okay. Let's see where we are. We have started with the general optimal control problem. And then we went through this linear quadratic optimal control problem. And we derived the control law. Now, I'm just going to use it, go one step further. This is what we have discussed. At time k, the optimal cost is this cost, is the terminal cost. At time n minus 1, the optimal cost is the minimization of this big quadratic function of u and x. We have derived the optimal control sequence u of n minus 1. Now, just go one step further here. If I plug in u n minus 1 to the optimal u n minus 1 to this guy, I'm going to get the optimal cost to go, which is I just substitute u, the optimal u n minus 1 to this function here. This is the result you're going to get. And the way to understand this is, again, by using the formula we just derived for the general basic quadratic function. It's going to be, let me bring up Let me bring up this. For those who are viewing from webcast, I'm just going to use this once again, okay? The optimal cost by doing the substitution here, remember this format. It's going to be -1 divided by 2, P transpose M inverse P plus Q. Now here, the optimal cost has to be, you see exactly this is happening. It's some kind of symmetric form. And then inside is some inverse of matrix, all right? You have seen how we derive this inverse matrix here. And then you see here, this is sort of the P here, this thing. Oops. Yeah, here. This is the matrix corresponding to here. And this whole thing is the vector P here. And on the side, I'm just doing, on this side, I'm just doing a transpose of this vector here. This transpose of this vector here. Now, there's one more term, right? This term. What do you think is the constant term in this big quadratic function? The term that's not dependent on u. What will be that constant term? Is this one, right? This is one of it. It's not all of it, right? This function, this term doesn't depend on u. And then look at this one. When I do this combination, this and this is going to create another term that's independent of u. And you see exactly this is what's happening here. This Qn minus 1 is this one. This A transpose SA is coming from here, right? A transpose SA. So you see exactly this, we're just using nothing but this result over here. Now, as a sort of notation convenience, I'm going to define the whole term, which is a quadratic function of xn minus 1 here as a basic, as a term. I'm going to wrap this up. I'm going to wrap the whole thing, the whole equation term as matrix Pn minus 1. Yeah. So this is what I will be denoting, just because I want it to has a structure in the analysis. At time n minus 1, the optimal cost is a quadratic function of xn. And at time n, and this is at time n minus 1, the optimal cost is a quadratic function of x of n minus 1. Now, I have defined, if you noticed, S as P of n, okay? And here I have S terms of S. So to make it more structured, I can substitute P of n, we substitute S with P of n in this function here, all right? Over here. Then I'm going to get this. I'm going to get this new notation here, okay? If you remember ME232, this is the Riccati equation. The quadratic equation that's connecting between Pn and Pn minus 1. We'll talk about how to understand the Riccati equation in a few more lectures. All right? So I can do the same thing. I can express the optimal state feedback law as a function of Pn and then x of n minus 1. You already know the importance of this control law and why it's convenient. It's because this whole term over here is a matrix. And then we are doing nothing but state feedback control. So doing state feedback control can let us achieve optimal LQ solution. So this is the main power and main message over here. I started with time n. I went to time n minus 1. But you can think about it. If I start at any time k, and I go backwards, k minus 1, the analysis will flow as well. This is the general steps of from k plus 1 to k. So if I started at k plus 1, I express the optimal cost to go at k plus 1 as a quadratic function of x of k plus 1, the P matrix P k plus 1. Then, just analogous as what I did, from n to n minus 1, we can get at time k, the optimal cost is a quadratic function of x with this Riccati equation, and then the optimal state feedback law. I did the analysis down here is for, it works for time varying matrices A, B, A and B. But we'll be focusing mostly on time invariant cases where A, B are constant. But the message here is kind of interesting. Think about how we're going to implement this control. By just looking at these equations, think about how we're going to implement, how we're going to do this. If I want to compute U, I'm going to need the system B and A. But I also need, what we define. But we're going to need pk plus 1. Now, if you need pk plus 1, put it back here. Pk plus 1 is going to require you pk plus 2. Now, iterate. Pk plus 2 depend on pk plus 3 and all the way to pn. So when you actually implement this, okay, this is a summary. Pk plus 1 depends on qk plus 2, and then pk plus 2, and then all the way. So when you actually implement this control law, actually u of 0 is going to depend on all the future p1 to pn minus 1, which, looking at this Riccati equation here, which is going to require us the knowledge of all the future Q matrix, A matrix, R matrix. Yeah, that's all. So this is what I said here, which is going to depend on all these future knowledges of A, B, R, Q. But this is no problem for us. It looks complicated, but it's no problem because these P, they can be computed offline, right? Because the P matrix doesn't depend on X. So we can compute these Riccati equations offline first, and we can obtain all the P1 to Pn minus 1. Then we can implement the control law online. So that's how the optimal solution is implemented online. All right. I'm going to use perhaps another 6 minutes to sort of discuss the most generally applied control law. So I'm doing here, this is sort of a long and slightly more complicated version of what we're going to implement in practice. In practice, ABR, Q, they're mostly, in the usual case, we let it to be constant. If we have advanced design, we can make it time varying. But these are usually constant. And then in practice, what we minimize is usually this final time n. In practice, we would usually take it to infinity. Say we're going to minimize the cost all the way in the future. In practice, what we do is what we call usually a infinite horizon discrete-time LQ. This is the easiest case. So instead of the previously finite horizon discrete-time LQ, we do infinite time horizon LQ. And then I'm going to review some properties of this design. Okay. This is a quick summary of what we have done in this lecture. Okay, this is for the time varying case. Now, if I assume if I assume time constant A and B, then let's see what will happen. So we have one example here, a second order system where the matrices A and B, they are time invariant. T here is 1, it's a sampling time. So this is a double integrator. The way to look at this is you look at the first term, x1. x1 of k plus 1 equals to, let me write it here, x1 k plus 1 equals to x1 of k plus t x2 of k plus t squared divided by 2 u of k. All right? So think about velocity and distance. The distance at next time interval is the previous distance plus the velocity times the time plus 1 divided by 2 t squared uk. Okay, consider this as an acceleration. Right? So this is a double integrator. And the performance index here, I'm using constant performance matrices Q and R over here. Q is a symmetric positive definite, positive semi-definite. R is positive. We're going to examine what this Riccati equation is going to give us. What's the solution of P is going to look like if I take, for example, different values of Pn. I take different values of the terminal condition. I just see how this is going to behave. And this is the result. So if I optimal horizon as 10, then I choose the final condition of P as 1, 1 over here, diagonal 1, 1. This is the solution of the Riccati equation. So it's going to go backwards. And then you see it sort of converges to something, right? This is doing nothing but solving this equation here. So this is the result. Now, let me mark these values it converges to. 8 and 3. Now, I'm going to change the final time horizon from 10 to 30. And then this is the converged values of P. 3 and 8. Now, if I keep the same time frame, and I change the terminal condition from this to this. Okay, you see, it's this 2 and 0, from this to this. Again, you see it's converging to something, 3 and 8. They are all converging to the same thing, regardless of how I initialize the terminal condition. So some observations is because of this, we can infinite time horizon LQ very easily. So first of all, PK is indeed always symmetric. It's converging to, it's a little bit difficult to see here, but you see 2 of the elements converges to 3, and 2 other elements converge to 8. So if you really plot it, it's symmetric. Now, regardless of the boundary condition, P of n, the solution of the Riccati equation converges to the same steady state value, right? Even for this very simple problem, well, the time frame, I'm just considering the cost in the future 30 time steps. It converges to this constant value very quickly. So this is saying for the majority of times, we are actually implementing a constant value of P. So because of that, the control law, you see, is converging to a constant state feedback control law. Instead of this big time varying matrix P, we have a time varying matrix P, and here a time invariant matrix P. This is going to save a lot of computations, as you can imagine. All right? This is an introduction of why infinite horizon LQ and why constant matrices can be applied in LQ. right? We're going to talk about details. We're going to talk about why it actually converges. We can actually prove that this will hold. We can prove that this will happen under certain conditions. All right, so that will be the end of this lecture. See you on Thursday.